Okay, so let's take a look together. If you have any questions before we start, you can ask. Okay, I returned the midterm, the graded midterm examination, yesterday, last night, and I think for most of you, the scores are okay, except there's one person that didn't do so well. Okay, and so I'm gonna help a little bit. So basically, for the person who didn't do very well, uh, you can redo some of the problems and then submit it to me by Friday as announced. However, the scores will not be 100% of them of the scores. Okay, it's gonna be at most half, and this is because generally for graduate level we don't give the grade below B, and so this is a way, so that you can at least get the minimum grade, for the graduate level. Okay, and but most of you have done well, so I guess it should be okay. Okay. Okay, so we're going to spend the next two lectures on support vector machines. Depending on how much I finish today, if I finish a lot and then I only have some small remaining part, I may record a video so that you can watch over the New Year week, next week. Okay. And this is so that after New Year, after the Thai New Year, Ajahn Lin, Dr. Lin can start the neural network topics. Okay. But if I don't finish SVM very much today, I will need to continue the week after Thai New Year, and then Dr. Lin will start the neural network after that. And I think Dr. Lin he's going to spend about 3 weeks on the neural network, plus LSTM and all that. So okay, let's do it. So what is support vector machine? Support vector machine is a type of classifier, okay, meaning that it is used to classify the data into uh, two types or three types. They can extend it to not just binary classifier, but it can be non-binary classifier. However, generally when you study or look at the support vector machine, we often look at binary type, for example. Okay. And in short, we often call it SVM, which is the support vector machines. Okay. So what is support vector machine in general? So let's consider this image. Well, I was actually going to try to draw some of these in advance, but I didn't have time. So let's do what we can do, okay? So generally, if you are given two sets of data, let's say you have two types of data. Ah, yes, let's say it's two type of data like this. So the blue colors will represent one class of data. The other will be used for the other type of data type. Okay. So, um, so, so basically, when you have this type of data, we can call it as vectors, data vectors. Okay. And in support vector machine, what it's trying to do is it's trying to draw some type of boundary between these data type, between these data in different classes. Okay. And it's trying to maximize the margin. okay, and this is called margin, okay, between these two type of data. Okay, let's call this as class 1. This is as class 0, for example. Okay, we can call that. So if the boundary is linear, then we can call it like the linear type. So it's up to us on how to classify it. Okay, but on the other hand, if the boundary is not linear, but maybe it looks like curves. Okay, some type of curves like these. You don't need to draw all the points. Okay, I just draw it as some part, some illustration. So if these classes, they are not like uh, they are not linear separable, then the boundary will be curved. And it can be defined by different types of nonlinear function. And so this is often called nonlinear. Okay, and so the linear type is the simple type. Okay, while the nonlinear type is a more useful type. And nonlinear type is often concerned with what is so-called kernel. Okay, we'll take a look at it a little bit later. Okay, and in addition to this, there are also some other types of key parameters involved when people talk about SVM. Mhm. Well, by the way, I have to emphasize that when you look at the SVM is the SVM and decision trees. They are different from EM algorithm or k-means clustering and all that. Because for SVM, it is similar to decision tree algorithm, meaning that they are supervised learning. Okay, so meaning that you have some data for training, and you have some data that are used for validating, or sometimes uh, people call prediction. Okay, this is different from this type of some the types of algorithm, the unsupervised learning algorithms like the EM algorithms or k-means clustering. In that case, you just classify without knowing actually what the actual classes each data point belongs. Okay, so for supervised learning, you need to know for the training data, you need to know the classes that you need to assign classes, and then you train in order to build model. Okay, and when people talk about SVM, I'm not gonna go into mathematics yet. After this, I'll go into more deep mathematics. Okay, and in general, when people talk about SVM, there are also some other parameters that people talk about. One is called C parameters, or some people call it what is it? Regularization parameters. Okay, and so basically, C parameters, it helps allows some errors during classification. Okay, so meaning that, for example, if you have data like this, okay, and maybe when you try to separate the data, there are some data that may not fit into the uh, on the right side of the boundary always. Okay. Okay. So here there will be some data points that you know uh, occur on the wrong side. Okay. And the C parameter helps you allow such errors to occur. This is so that you can build a model, and it makes sense to build such model. Okay. When you have some data that the data points, they don't separate from each other 100%, then if you don't allow such errors, your boundary will be very strange. You can try to make boundaries like this. Let me use a different colors. And then, which colors do I have here? Maybe blue colors. Yeah. I mean, instead of having linear boundary, you can have some boundary like this, you know, and another set is like this. Oops. So you can say this is class 0, this is class 1. But it's going to be very strange if you set boundary like this, because there are some errors that you have to try to make it 100%. Okay. So basically, the C parameters allows you to have some errors, allows you to have some errors during classification. Okay. And in general, if you have a low C, then you can allow more errors. Okay. If you have a high C, then you allow uh, fewer errors. Okay. So this is one parameters that people sometimes talk about. The other one is called the gamma parameters. The other one is called gamma parameters. Okay. This is different gamma from the EM. Okay. It's just the same variable, but it's very different. Um, so what is the gamma parameters? So for gamma parameters, what happens is when you have data points, okay, that are away from the boundaries. And let me draw the boundary as the orange colors. Let's say this is the boundaries. Okay. So for gamma parameters, it's related to what is called margin. Okay. So if you have low error, if you have low gamma, then this is for low gamma. Okay. Low gamma. Okay. For low gamma, you allow small margins from the support vectors to the boundaries. Okay. But then if you allow higher gamma, it means you allow to have more margins. Meaning that you can account for more points. Okay. So this is called for a higher gamma. Okay. So this is lower gamma. So you allow more margins. Okay. Okay. Also, the points where we used to build boundaries, we call support vectors. For example, this can be considered a support vector. Okay. And what does it support? Okay. It supports to build the boundaries. Okay. Depending on how many of them you want to use. Okay. The simple case is you want to use the support vectors that are so close together, a few of them. But if you use gamma that are higher, you allow more support vectors to be used for the construction of the boundaries. Okay. And in addition, when you do the training for this type of SVM algorithm, you can do linear type, you can do nonlinear type. Okay. Also, when you have higher gamma, sometimes when it's related to nonlinear SVM, for nonlinear SVM, mhm, it also means that you allows more curvatures. Okay, to the boundaries. Okay, and so meaning that when you have higher gamma, instead of having just a nonlinear curve like that to classify for the boundary, so you can have like a more curvy type. Okay, so this is the for higher gamma, and this is for lower gamma for nonlinear type uh, SVM. Okay, and when you do this type of classifying, we often set gamma to be between 0.001 and less than 10, while for the C parameters, we often set it to be between like zero point 0.1 to 100. And during the training, they used combination. They rotate or try different combination of gamma and C. Okay. Um, okay. Okay. So that's like a very introduction of what SVM is. So now let's take a look at what the algorithm is by itself so that we understand it a little bit deeper. Okay. Okay. So let's take a look at these pictures. Okay. Let me use the blue colors instead. Mhm. So let's consider these figures. Okay. Um, so if we have this type of points, okay, let's take a look at one uh, okay, one side of the data that you try to classify. Okay, if these points itself is support vector of one class, let's say it's class 0. Okay, then and if I let the boundaries as the orange colors to be this line, okay, you can draw a straight line as well. Let me change to straight line, maybe it looks a little bit easier. Okay. Okay, Let's say this is the boundary, which is the blue colors. Okay. And okay. And if we draw this line, that is the perpendicular to the boundaries. So this is the boundary. Okay. Then I can draw one vectors here. Okay. Let's call this thing as x. Okay. Um, so when we look at this type of pictures, what do we see? Well, basically, so this is the boundary that we are looking at. Okay. And the distance between x and the boundary, okay, can be computed like this. Okay. What we can do is, so if we want to find the distance between this x, okay, to the boundaries with respect to the origin, let's say this is the 0, 0. Okay. So what we can do is we can draw these vectors. Let's call it w. Okay. So let w, okay, be a weight vector that is perpendicular to the boundary. Okay. And so the distance between x, which is the support vector, and the boundaries can be found by having a projection of x onto w. Okay. And this thing is, if you project x onto w, we will have w dot x. Okay. Or in terms of metric, so this is called projection of x onto w. Okay. In the metrics analysis course, I think at that time, last semester, we defined it as w transposed times x. Okay. So it's quite similar. So this will be the distance between the support vector and the boundary. Okay. So this thing, okay, is equal to distance between uh, support vector x and the boundary. Okay. Sometimes, if we only look at one dimension or two dimension, it is very easy to draw boundary. Okay. But in general, for the boundary, we use the term hyperplanes. Okay. So hyperplane is just the name of boundary. Okay. And the dimension, if we have only two dimension on these pictures, the boundary is just a line, right? If you have x as three-dimensional, then so if x is just one-dimensional, okay, then the boundary will be just a dot. Okay. If x is two-dimensional, like in this case, we have a horizontal axis and the vertical axis. The boundary will be just line. Okay. If we have x as 3D, which is a little bit more difficult to draw, then you have like a plane. Okay. So here this is line. This is like point. This is like a plane. Okay. Then if you have higher and higher dimensional, let's say n dimensional, it's hard to draw, right? So we just call it hyperplane. And that's what we mean. Okay. So this is hyperplane. And and so the support vectors, there are two sides, one for one class 0, and then of course you have the let me draw with the red colors. You also have the support vectors on the other class, like class 1. Okay. You also have vectors around, and the closest one is called also called support vectors as well. So this will be also support vector for the other class. Okay. So let's go further. I don't know, just in case you forget what projection is. So let's do a very quick review what it is. Okay. So if we have a vectors w and we have vector x, okay, that you project onto w, like on the previous page, okay. So this vector that you project onto is called w times w dot x, okay. So this line is going to be perpendicular to w with the angle of theta. Okay, this is from the matrix analysis course. Okay, here you can write as w dot x, like a typical vector, or in the matrix form, you can write it as w no, w transpose. W is a vector times x. Okay, if we write it as a matrix or vector, w can be set to something like let's say it's n dimensional. You can have w1, w2, wn. Okay, and x similarly, x is equal to x1, x2, all the way to xn. This is how we define it. Okay, and so w transpose times x is nothing but w1 x1 plus w2 x2 all the way to wn xn. Okay, or we can write it as summation of wi xi, I is equal to 1 to n. Okay, so you can write it like that also. um, in addition, if you want to know the cosine theta, cosine theta is computed from w transpose x divided by the size of x times the size of w. Okay. where the size or the length of x is defined by square root of x1 square plus x2 square all the way to xn square. Okay. Um, or you can write it as square root of x x transpose times x. Okay, it's the same thing. So this is a quick review of the notation that we have seen before in the past. Okay. Okay. So let's take a look then. So let's continue from the previous pictures that we saw earlier. Okay. So uh, on the previous page, we defined what is called a hyperplane, right? Which is just the boundary. Okay. And in general, we can look at this picture as follow. So let's say this as the data on this class on the right side of the boundary. Okay. And let's call this one as a support vector because it's closest to the boundary. Okay. So this will be a support vector to build the boundaries. Okay. And on the previous page, we have that. Uh, if we draw these, okay, from the origin perpendicular here, this is I call this a vector of x. Okay. And for the weight, so this is w. Okay. Mhm. So to build a hyperplane, we can also call this the vector. We can call the length of this the part as a b. Okay. So in general, we define that for a hyperplane, okay, for a hyperplane or the boundaries between the uh, uh, support vector machine and the boundary. Okay, so we can write the condition of this hyperplane as the projection of x onto w. Okay, or we can write it as w dot x. Okay, and one moment, I need to define another thing as well. Okay. Okay. So this size is the size of the projection. If you add the bias, let's say this is on the right side. When you add bias, you get 0. Okay. This is how we define it. You can put minus b instead of plus b. It doesn't matter. Okay. And I think if you look at in literature, sometimes instead of writing like this, they write it like this as well. They write it in terms of another notation as well. If I look in here, let me rewrite it, otherwise it's a bit strange. So instead of writing like this, uh, we can write these or these together, right? Oops. Transpose times x. We can also write it like this. W and then x. Okay. or you can write it. We can also use another notation as w vector comma x vector. Okay, and you will see that this the dot product or the multiplication of vector. This is just the numbers. Okay, so we can write it like this. It's okay. We can write it like this. It's okay. Or you can write it like this, or you can write it like this. Okay. If you write it like this, we call mathematically we call it inner product. You can also call it size, and not size. You can call it as the how do you call it? You can call it as, yeah, we can call it inner product. Okay. Or for this one, we can write it as square root of x comma x. Okay. So the size or the length or the size can be found from square root of inner product. Okay. Like I mentioned, you can write it differently, but this is how it's usually defined. Okay. So that means that if I use this notation here, I can write it as um, plus b. Okay. Equal to 0. Okay. You can use either notation. Doesn't matter. Okay. And what else? Okay, let's look at an example of this, just this type of equation, what it means. Okay. Okay. And for example, um, if you are given that W is uh, is 1 1 and X is equal to 2 4. Okay. From the previous equation is written as like this. What does that mean? It means is W transpose times X plus B is equal to 0. Okay. Or we can write it as W transpose times X. Okay. Remember that this is like a size of the projection, and then plus B equal to 0. Okay. So if you multiply together, you get 1 times 2, you get 2 plus 1 times 4, which is 4. Okay. And then you plus B to be 0. Okay. So for this case, it means that B is going to be equal to minus 6. So that's all what it means for this type of equations. Okay. Similarly, if I still let X in, you can call X as a support vector, which is still 2 4. Okay. But if I let W to be a different vector, different weights, let's say it's 2 2. Okay. If I use the same equation, I'm gonna get something like 2 times 2 is 4, plus 2 times 4 is 8, plus b equal to 0. Okay. So in this case, I'm gonna get b equal to minus 12. Okay. So it means that for a given support vector, okay, there are many choices of W and choices of B. This B in SVM we call bias. Okay, so that many cases. Okay, there are many choices of W vector, and there are many choices of bias that you can satisfy this type of equation. Okay? So because there are many choices, so what do we do? So in general, what do we do is we try to maximize the margin. Okay. So let's take a look at these pictures. We're still looking at the linear type, okay? Just for simplicity. Let's say that on this side, we have these data points. Okay. We are looking at an ideal case, no errors whatsoever yet. And then on the other class, we have something like this. Okay. And this is the support vector of one class. This is the support vector from the other class. Okay. So you can sort of guess that we try to look at the vectors that are so close together, right? And so and this is called the margin, the distance between support vector to the boundary. This is called margin. This is also margin. Okay. So with many weights and many bias that are possible, okay. So we will try to choose the hyperplane or the boundary that gives you the maximum margin. Okay. And then if you take a look at these pictures, there are two dotted lines. Okay. As this dotted line, they are not the hyperplane. Okay. So instead of having the relationship of Wx, inner product of Wx plus b to be 0, okay. So we can set some value to it. For example, it is equal to positive values. Let's say this is class 1 or class positive, and the left hand side is class 0 or class negative. Okay. So for this line that cuts, that intersects with the support vectors, okay, from the left hand side, we can write it as Wx plus the bias, but instead of here, this one equals 0. But then on the right hand side, we can set just some positive value, for example, plus 1. And on the left hand side, we can put negative value, or let's say minus 1. Okay. Well, it turns out that this d, or the distance, this is the distance or the margin, is going to be equal to 1 over the size of the weight vector, which will be proved later. Okay. So in general, if you maximize this distance d is the same as minimizing the size of vector w. Okay. Okay, let's continue. We'll have some example a little bit after. Okay. So basically, in order to build such a model, we want to minimize the size of W. But in practice or in analysis, instead of minimizing the size of W, okay, we will minimize the size of W square instead. Okay, just because it is simpler, it's easier in terms of mathematics. Okay, you can call this as a cost function as well. Okay, and we want to minimize this the size of the weight vectors squared with the condition. So this is the condition. You can say subject to what condition? Subject to the condition that the inner product of W and X plus B. Okay. From the previous page, there are two cases. One is equal to 1 and the other one is equal to minus 1. Okay. So if I let yi to be the target for xi, okay, let's say that because it's a binary, right? So if you look at this case, let's say that this is the x1 and let's call this is x2. Okay, so x1 and x2 are just the data at the support vectors. Okay, and then for the target values, so y2, I give it -1, and for the for the case 1, I let the target to be 1. Okay, so in general we can let the target to be yi is equal to 1 or -1 depending on the class, if it's class positive or class negative. Okay, and we need to know this because we need to know the the class of each vectors. Okay, but these are for the support vectors only. So it means that there are two equations, right? Here and here. I go a little bit slow so that we follow together. So we have this as one equation, and this is another equation. Okay. If I multiply y to the front, in this case, y is equal to 1. So the whole thing, when I multiply, I just get 1. Okay. For this case, y is -1. If I multiply whole thing with y, -1 times -1, on this side, I will get +1. Okay. So if you look in many proof that people look at, they don't talk about it very detail. Okay. So that's why I want to go in a little bit more detail. When you do modeling, it just compute the weight, the bias, and so on. But in the analysis, it's a little bit more involved. Okay. So it means that the condition that we have is instead of having two equations for the conditions, we just multiply yi. Okay. This one I call xi and let it to be equal to and I will make the condition to be greater than or equal to 1. Okay, it can be larger, it's fine. Okay, so this is the the optimization to find W. So this is the optimization, okay, to find the weight. Okay, and here where yi is equal to 1 or -1 depending on what class we are looking at. Okay, if we're looking at the support vector which is positive, then this is 1. If the support vector is negative type, this is the -1. Okay, or you can say that this is for class 1, this is for class 0. Okay, you can call it that way as well. So let's take a look how to find the margin. Okay, so let's take a look at these pictures together. So let's say that we have two support vectors of class 0 and class 1. Okay, let's say this is the support vector for class 0, and this is the support vector for class 1. Okay, so for this one I can write it as x plus, and then for the support vector of the class 0 I can call it, I can write it as x minus. Okay, so if we draw like this, we can draw the boundaries. Let me use this a boundary. Okay, okay, and the boundary is gonna be in the middle, right, uh, between this line and this line. Okay, so what is this width? Okay, what is this width? If I draw a vector for x minus, so this is x minus, no? So this will be a vector for x minus. Let me use the blue, I can use the red colors here. So this is the vector of x minus, which is the support vector for class 0. Okay. And let's call this as the vector of x plus, which is a support vector for class positive. Okay. If I want to find this length, let's use the blue colors. If I want to find this size, which is 2D, okay, I can just draw these vectors. Okay. This vector is going to be called x plus minus x minus. Okay. If you remember how to draw this vector, if you have x plus like this, okay, and this is x minus, this is x plus, this is x minus, okay, x plus minus x minus, x, to have minus x minus, you can just draw like this. Let me use the red colors. Okay, this is x minus x minus. Okay, if you add these two, x plus minus x minus, you get something like this. Okay, or similarly is this line. Okay, but then if we want to find this width, we want to project, so we can project x plus minus x minus, which is this the blue line, onto the vector that is perpendicular to the to this the boundary line or this line. So if I call this as W, okay, then we can, if we want to find the length, this can be very long, no? But I just draw it like this. So we can project x plus minus x minus onto W. Okay. And the size of it, okay, will represent the width that we want to look at. So this is the width between two support vectors, or it is equal to 2D. Okay. So it's going to be projection of uh, x plus minus x minus. Okay. You can write two ways. You can use W first, or you can use x plus minus x minus at the front. Doesn't matter. Times W. Okay. And then normalize by the size of W. Okay. This is so that W over the size of W becomes like a single unit unit vectors. Okay. And how do we find this? So let's put a star here. Okay. Well, from previously, we have that. So previously, we have this equation for these two lines. Let's call this is A. Let's call this as a B. Okay. So for A, we have inner product of Wx plus, this is for the class positive. Okay. And then plus the B equals to 1. Okay. And okay, or I can write it as the W dot X plus just the matrix multiply to each other, right? This one will be equal to 1 minus B. Okay, let's call this equation 1. Similarly, for uh, the line on the left, so A is this line, B is this line. I can write it as Wx plus, or the x minus. Okay, and okay, plus B equals to minus 1. Okay, so this one I'm gonna have W dot x minus equal to 1 minus 1 minus B. Okay, so I have these two equations from the line on the left and line on the right. Okay, so if I replace 1 and 2 into this equation, okay, if I uh, insert 1 and 2 in this asterisk equation, what am I gonna have? Okay, I'm gonna have that the width, or 2D, on the numerator, I can write it. I can expand the product to get x plus multiply with W, and then minus x minus multiply with W. Okay, and the whole thing is 1 over size of W. Okay, so what I do is I just expand the top part here. inner product, you can distribute the term. Okay. So from equation 1 and 2, then what do I have? This one is from equation 1. I just get 1 minus b. And for this one is from equation 2. I just get minus 1 minus b and multiplied 1 over size of w. Okay. And this thing is 2d. Okay. So if you look at it, you get 2d is equal to 1 minus 1, you get 2, minus b plus b, you get 0, and divided by size of w. Okay. So therefore, you have that the half, the margin, this one is called margin, is equal to 1 over w. Okay. So if you look in many work that they try to analyze, sometimes they skip many parts in here. So this is like a detailed way of proving. Okay. Now let's take a look a little bit more. Okay, on how to find the W thing, because we don't have the weight yet. Okay, what how do you find it? Okay, so in general, we need to convert the problem using what is called Lagrange theorem. So to find W, we need to exploit or use Lagrange uh, property, or Lagrange. I call it property. So there's no need to prove. Okay. So in general, during training, okay, so we will have data points of x, and then xi, and then yi. Yi is the target, what class it is. Okay. And we will also set another parameters called lambda to be positive, to be non-negative. Okay. And so in the Lagrange method, which is a way to do optimization, is that, so when you have the cost function, or here it's called Lagrange function. So Lagrange function is trying to is used to optimize and try to find the lowest possible errors. Okay. So in general, we try to minimize the Lagrange function. Okay. And in here, the Lagrange function is actually very similar to the cost function. It depends on the parameters, weight, bias, and also the alpha. Okay. As there can be many alpha, we can define alpha as alpha 1, alpha 2, blah, 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 until alpha n. Okay. And these are the alpha for the support vectors. If there are only two support vectors, then you only have alpha 1 and alpha 2. Okay. So for the Lagrange method, what it's doing is it's trying to minimize this function, which is the cost function. But here we will write it as 1/2 of the weight vectors. Okay. And we will also subtract it with the condition, because here we try to we have the condition of yi multiply with w and then xi Okay, and plus b, okay, which is equal to 1. So we put minus 1 here. And here we add the alpha parameters. And the summation is just is the sum. Okay. So the right hand side is it comes from the condition from the previous condition for the optimization. Okay. So in the Lagrange algorithm, it is trying to minimize the Lagrange function with respect to W and then B. Okay. Let's call this the Let's call this the equation 3. Okay. So in order to minimize this type of function, we we minimize it with respect to the weight and also the bias. Okay. So what we can do is we can differentiate L with W and with B. Okay. If you differentiate L, if you differentiate this function with W, you will notice that this term, okay, what you will have is you will have something called W, okay, because this W size of W square is just W transpose times W, okay. And in terms of metrics, when you differentiate with respect to W, you get one W left, okay. And then on the right side, if you differentiate with W, what you have left is summation of alpha y times x. Okay, and the b and minus 1, they're all gone. Because if you distribute this term, um, the b and minus 1 doesn't have w in there. Okay? So when you do differentiation with the L, this is what you get. So the first term, you have this w vector or w vectors. And then minus the remaining term on the right hand side. It's just summation of alpha I, yi, and then xi. Okay. And then we can set this to be 0 because after differentiation, we set to be 0. So it means that the weight can be found from summation of alpha I, yi. Alpha and y, they are just scalar, and xi. Okay. And if we differentiate L similarly with B, we get even simpler term. Okay, so this I is equal to 1 to n. This is number of support vectors. Okay, if you differentiate L, the minimization value with B, first term. Okay, first term you differentiate with B, you get 0 because there's no B in here. You differentiate second term with B, all you have is just summation of alpha times y times b. You differentiate with b, the b term disappear. Okay, so when you differentiate with b, all you have left is summation of alpha I, yi, okay, and minus term at the front. So if you set this differentiation to be 0, it means you get summation of alpha I times yi has to be 0. Okay. So this is a second condition. Let's call this as equation 4 and equation 5. Okay. Anyway, so it's already almost 6. Okay, let's take a break, maybe 10 minutes, and come back. So when we come back, we will, let's see. I don't know whether I will expand the equations very deep, but I can try to do that. And then we will have some example on the, the compute, the some computational approach, what we have. Okay. So let's have a break for maybe 10 minutes and then come back. Okay. Okay, let's continue from the previous derivation. Okay, so before the break, we have this type of expression that from the optimization, you will get this type of uh, results that the weights can be found from the targets, the support vectors, and also this uh, parameter called alpha. Okay. We also will get the condition that the alpha, when it's added together with multiply with the target for each support vector, sum together you get 0. Okay. So it means that we can reduce the Lagrangian function as follow. So we can simplify Lagrangian function to like this. Okay. So previously we wrote the Lagrangian function as 1 over 2 size of vector squared, vector the weight vector square, and then minus summation of alpha I times yi w dot xi, and then plus b, and then minus 1. Okay. So previously we wrote it like that. Okay. And sorry, this y has to multiply wx plus b. Okay. So if we let w to be what we had on the previous page, so this w is summation of alpha I, yi, xi vector. Uh, okay. We can replace this w in here with the same equation 4 from the previous page. Okay. So let's see what we will have. So we will have 1/2. Well, we know that size of w square is equal to w times w, right? Okay. So here we can write it as two term. One is summation alpha I yi xi vector and multiply with another w. But when we multiply like this, we need to change the variable from I to j. So that is easier to multiply. Okay. And then minus the term at the back, which is summation of, oops, alpha I, okay, multiplied with yi multiply with w, which is summation alpha I, yi, xi. This is w, no? And multiply with also because we have 2y, so let's call this as j. We change the index to j instead. Okay. Whenever we have two summation multiply together, we will change one term to be a different index. Okay, so that it is easier to see, and multiply with xi. Okay, and then add it with um, um, actually we can expand. So this thing is summation of alpha I times this term, but so I can put like this. Okay, and then I have minus, and then I have minus summation alpha I yi multiply with b, and multiply with b. Okay, uh, I they are here, so I can put parentheses and then multiply with b. And then at the end I add it with plus summation of minus times minus 1 is plus summation of alpha I. Okay, so for the first term, this thing, when we multiply something like this, we can just write down 1 over 2 summation I summation j alpha I alpha j yi yj xi xj. By the way, I don't need to go this detail, but if you look at in many books or many works, they explain in this way. And if we derive together like this, then you will understand what it means. So basically, we earlier we had the Lagrangian function, uh, which is from here, which is here, okay? But this Lagrangian function has three parameters involved, okay? So what we did was we differentiate with w and with b to determine equation 4 and 5, okay? And then we use this property in equation 4 and 5, plug it back to equation 3 in order to simplify the Lagrangian function. Okay, and you will see later here, after we simplify it, this Lagrangian function will only depends on the unknown alpha. Okay. Okay. So for the first term, I write it as 1/2 summation I summation j alpha I alpha j uh, yi yj and then xi and then xj. Okay. And then minus, so this term, similarly, we have summation alpha I, we have summation alpha j. We can group terms together. Okay, we can write it as alpha I alpha j. Okay, here you have yi yj xi xj as well. Okay, so we can write it as yi yj xi xj as well. Okay, and then how about this term? This term from equation 5, summation of alpha I yi is just a 0. Okay. And then you add it with summation of alpha I. Okay. And then you notice that the first term and the second term, they look very similar, right? But one has the scale of one half, the other one is -1. So here what we will have is we will have this L function depending on alpha. This the optimization function is summation alpha I. So I write alpha I here at the front and minus only the leftover from this one half -1. I guessed -1/2 summation I summation j alpha I alpha j y x I x j. Okay, so that's it. So this is the Lagrangian function. Okay, and so basically we can uh, we can minimize this term with respect to alpha. Okay, and also subject to the condition subject to the condition which is 1 alpha I is greater than or equal to 0 and 2 summation alpha I yi is equal to 0. Okay, and from this optimization you will get what is called alpha I. Okay, and for this optimization it can be used by many existing algorithms to find this alpha I values. Okay, and once you get the alpha I, okay, we can find uh, the weight vectors as summation of alpha I yi and then support vectors or the support vectors. For the bias, it is equal to y for each bias we can get it from yk minus w and then xk. Okay, so and this is how we compute it. Okay, okay, so let's look at an example of numbers. Okay, so let's say that we are given the following support vectors. Xi, okay, as well as the target yi, as well as alpha I obtained from optimization. Okay, then what? Well, let's say we have this data, say x1 equals to 1, 1, 2. This is a three-dimensional. The target for this support vector is 1. Alpha 1 is equal to 3. Okay. And then for the second support vector, let's say it is the -2, 1, 0. Y2 is class negative, which is -1. And alpha 2 is 2. And x3, the third support vector is 0 to 1. Y3 is equal to 1. And alpha 3 is equal to 0. Okay. So given these values, we can find the weight. Okay. So the weight vector from the previous formula we have is equal to summation of alpha I, yi, and then xi. Okay. But here there are three support vectors. Okay. So we have alpha 1. Alpha 1 is 3 times y1, which is 1, times 1, 1, 2. Okay. You can also write it in the vector form. That is also possible. Add it with alpha 2 times y2 and the support vector number 2, which is minus 2, 1, 0, and add it with alpha 3, which is 0, multiply with 1, and the third support vector, 0 to 1. Okay. So here you will have, what is it? 3 times 3, 3, 6. Okay. Minus 2 plus 4. Minus 2 times 1 is minus 2 and 0. And for the last term, because we have 0 here, right? So the whole thing becomes 0. Okay. So when you add it together, what do you get? You get 7 minus 1 and then 6. Okay. So so this will be the weight vectors. Okay.
716 acha.
Says 716. Sorry. Yes. And to find the bias, we have three bias, right? Let's say I compute bias 1. So B1 is just Y1 and then minus the projection of W onto X1. Okay. Which is Y1 is 1. Okay. And minus 716 and then times x1. X1 is 112. Okay. So we get 1 minus 7 times 1. 7 plus 1 is 8. 8 plus 8 is 16. So I have 1 minus 16. So the first bias is minus 15, which is 1 minus 16. Okay. And you can compute, B2, B3, as follow as well. Okay. And so this is how is the computed. Okay. And let's take a look at, I don't think I have time to look at the kernel. Okay. We'll look at the example at the end. Okay. So let's go to very quickly. Woo, actually, there's a lot of things in here on the kernel, but maybe less than half an hour more. Maybe I'll make a small clip so that you can take a look at it. Okay, not so long, but it's gonna take you over 7 p.m. Okay, so let's go to an example for the linear SVM first. Okay. I share with you some links. I hope you can look at it. We can look at the second one actually. Yeah, this is the second one. No? So let's take a look at the Python code together. It's quite a long code actually. But let me see how long is it. Not so long. Okay. Okay. So here it's quite similar to last time. Last time, when we used those type of uh, library for the decision tree, we import to sklearn, right? And we import the decision tree classifier. Okay, but today we're going to use this library. This is NumPy. We will import this library that will make data into different groups of data. It's called make blobs. Also, this one similar to last time. In the model selection, we import this library to split data between train and test. This is for plot, you've seen it. And then for SVM, we will import from sklearn .svm. And in this case, we import linear svc. Okay. If we do the nonlinear function, we can import similarly. But let me see, it's down here. Okay. Or we can just import svc library also. Here, if you use import SVC, you can set the model as linear or non-linear, depending on what you want. Okay. So let's take a look at this first. Okay. And for this one, similar to last time, is the confusion matrix. Okay. So let's take a look at some codes together. So first, we can start by generating the the data between two sets of data. So we use the function called make blobs, and number of points is 250. The standard deviation is zero point 0.6. Okay, and there are two centers. So we can make more than two sets. We can make three sets, four sets as well. So for here, I generate x and y. Okay, and I think it will make two classes. One is class one, the other one is class 0. Okay, and so okay, so we can run this command. Also, take a look in the commands here. I set the class 0 to be -1 for use later. Okay. Oh, sorry, I forgot to run the first one. Let me see. I think they have different version. I think you need to install this the
Okay.
sklearn. Yes.
Uh, it's sklearn or datasets only.
Say again. Hmm?
It's only from the library sklearn or datasets.
Yeah, yeah. You don't need something like this, right?
Yes.
Yeah. Oh, you're right. Okay. Yeah, this is from the old version. Okay. And then okay, so this one's passed. So let's run these. Yeah. So then you get this data. Okay. So these are 100 and so we get 250 points and each one has different classes. Okay. And then I set the class 0 to be -1 in order to plot to look at it. And and also there the data that we generate for X, there are two columns. Okay. Column 0 and column 1. So I use a scatter plot. And for this color, you can change, to season, or you can input your own colors. That's fine as well. Okay. So if I click on the plot.scatter, you get these two sets. Okay. So in here, I don't use very large standard deviation, so the data they don't overlap. If I use the higher standard deviation, you will get this data that will overlap each other. Okay, then we have more errors and so on. Okay, and then similar to last time, we can use the train test split. Okay, and so we can split it. And okay, and then use the linear SVC to do the training, to basically to set up the model. Okay. Okay. So when it's done, so we have this SVC as the model. Okay. So these commands we just plot it and then try to how do you say it? We plot this to this data. Okay, and then try to plot the boundary and also these values. Okay, of course there's still errors, and let's see. So if you plot it, you get something like this. You can play around with this function, linear SVC as well, because you can set different parameters in there that you can play with. Okay, so if you run it, you get some plots like this. Okay, and you can also use the dot predict. This is similar to the decision tree. So you can so here I use the test data part uh, as a get the result as the prediction, and you similar to last time, use the confusion matrix to plot the uh, uh, to display the confusion matrix. Okay, and that's it. Yeah, so this part you see that there's no errors. So the correct for class 1, class 0 is 29, and class 1 is 34. Okay, and there's no error in between. Okay, uh, at the bottom, am I gonna show something here? Actually it's quite similar, so this part is okay. Uh-huh. And for the next one, this one is nonlinear. The nonlinear, you can also play around with this code as well. So for this code, let me see, what am I trying to do? You can play with the codes, but I will see if I can. It's okay. I will take a look at this next time when I look at the nonlinear classifiers. Okay. So instead of using linear classifier, you can also use nonlinear classifier, meaning that when you have data that are not here, when you have data that are sometimes curvy, or the data that are not so easy to be separated by the linear function, this one still looks okay. You can decide to use like nonlinear classifier as well. And there are different types to it on what to do. Okay. So next time we will, I think I will talk about it. Let me see. Okay, I think I will try to record some clip, and then you can take a look at it next week. 1 hour, maybe a little bit over 1 hour is enough, and then you can play around with this code from the clip as well, so that after New Year, Dr. Lin can uh, work with you on the neural network. Okay. And actually, for SVM, you may have heard of the parameters like the C parameters, the gamma parameters that we mentioned earlier. So next time I will talk about how to set this value in the code. And actually, in many literature, when you want to optimize the Lagrangian function together with these gamma parameters or C parameters or even slack parameters, or even for the nonlinear kernel, we will modify the Lagrangian function slightly. Okay, but the concept is still the same. And from there, then you are able to obtain the alpha values, then to obtain the weight coefficients, and also the bias as well. Um, However, if you look at the nonlinear kernel, sometimes you have some other additional parameters related to the nonlinear function as well. So that will also be found through the optimization Lagrangian function. Okay. So, okay. So this is it. I hope it's not too mathematical. A lot of people, when they talk about SVM, they talk about the very generic idea, but they don't go deep into the optimization or the Lagrangian function. So I hope it is useful for you, especially when you go and look at some papers, and try to understand the very super detail about the algorithm. Okay. You have any question at all? Does anyone have any question? I hope I didn't go through very quickly. I was trying to go very, very slowly as well. But I think you probably will get some ideas, right, on what we are trying to do. Okay, as you will see that for the SVM, we don't use much of the probability knowledge, but we use more knowledge on the matrix analysis. Okay, and uh, and in the derivation, we only use basically the projection, which is the quite a simple idea, right? And what else? I think that's about it today. Okay. Okay. So that's that. Okay. Any question before we leave? So in the video that I will send you in the clip is gonna be very about less than 1 hour on the nonlinear kernel and also how to use it. Okay. If I have other examples that may be a bit easy to follow as well, I'll try to find some example for you. Okay. Any question at all? G, you have any question? You work with SVM a lot, right?
Yes, Ajahn.
Do you follow the derivation well?
Yes.
No question at all?
I will ask Ajahn later, Ajahn.
Okay. 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 Have a good evening, everyone. Okay. Okay. I'll see you in the future.
ขอบคุณครับ
ครับ
Thank you อาจารย์
สวัสดีครับ
Thank you สวัสดีค
Yeah,
รับ
if you have any question, you can ask. No, I'll stay around maybe 5 more minutes.